I want you to do something for me right now. Hold your hand up in front of your face. Look at the space between your fingers. That gap, that apparently empty region between your index finger and your middle finger looks like nothing. It looks like the absence of everything. No matter, no substance, no content of any kind. Just a transparent void through which you can see whatever is behind your hand. I want to tell you that what you are looking at is one of the most violent, most energetic, most densely packed environments in the entire universe. That the space between your fingers is seething. That it is churning with activity at a scale so small and so fast that no instrument we have ever built can directly observe it. That the nothing you are looking at is not nothing. That it has never been nothing. That the concept of truly empty space, a region of the universe with absolutely no content whatsoever, is not just something we have failed to find. It is something that the laws of physics make absolutely, provably, mathematically impossible. This is not a metaphor. This is not a poetic way of saying that space has interesting properties. This is a hard result from the hardest theory in physics, quantum field theory, the framework that underlies everything we know about matter and forces, the theory whose predictions have been confirmed to greater precision than any other theory in the history of human knowledge. That theory says, without ambiguity, without escape, without any loophole we have been able to find in 100 years of looking, that empty space cannot exist. And the consequences of that impossibility go much further than most people realize. They go all the way to the question of why the universe exists at all, why it looks the way it does, why there is something rather than nothing, and why the something that exists has the particular character it has. The impossibility of empty space is not a curiosity at the edge of physics. It is right at the center of the deepest unsolved problems we have. Let me build this up from the beginning, because the argument has several layers and each one is important. Start with what physicists mean when they talk about a vacuum. In everyday language, vacuum means empty space, the absence of matter. You create a vacuum by pumping air out of a container, removing the molecules until there's nothing left. In physics, the vacuum is defined more precisely. The vacuum is the lowest energy state of a physical system. It is not just the absence of particles. It is the state with no particles, no radiation, no energy of any kind above the minimum. It is the ground state of the universe. For most of the history of physics, this ground state was assumed to be nothing. Zero energy. Zero content. A mathematical blank slate from which you could build up the description of matter and fields by adding particles and energy. The vacuum was the starting point, and the starting point was empty. Quantum mechanics changed that completely. Here is the key insight, and I want to state it as precisely as I can because it is the foundation of everything that follows. In quantum mechanics, there is a fundamental principle called the Heisenberg uncertainty principle. You have probably heard of it. It is usually described as saying that you cannot simultaneously know the exact position and exact momentum of a particle. The more precisely you know one, the less precisely you can know the other. But that is only the most familiar version of the uncertainty principle. There is another version, equally fundamental, that applies not to position and momentum, but to energy and time. The energy-time uncertainty principle says this: the energy of a system at any given moment cannot be exactly defined. If you try to measure the energy of a system over a very short time interval, the uncertainty in your measurement of the energy is inversely proportional to the length of that time interval. The shorter the time, the larger the uncertainty in the energy. Now, apply this to the vacuum. The vacuum is supposed to have zero energy. But the uncertainty principle says that energy cannot be exactly zero over a finite time interval. If the energy were exactly zero, you could specify it with perfect precision, and the uncertainty would be zero, which the uncertainty principle forbids. Therefore, the energy of the vacuum cannot be exactly zero. It must fluctuate. It must deviate from zero randomly, constantly, on timescales so short that they are almost unimaginable. These fluctuations are not artifacts of measurement. They are not imprecisions in our instruments. They are real physical events happening in the fabric of space itself. They are called quantum vacuum fluctuations, or sometimes zero-point fluctuations, and they have consequences that we can measure with extraordinary precision. Here's the most vivid way to think about what is happening. Quantum field theory describes all particles as excitations of underlying fields. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. The Higgs boson is an excitation of the Higgs field. Every particle we know corresponds to a quantum field that permeates all of space. And every one of these fields, even in its ground state, even when there are no particles present, has these zero-point fluctuations, these irreducible quantum jitters that the uncertainty principle makes unavoidable. What this means is that the vacuum is not empty. It is a seething ocean of fields in their ground states, each one fluctuating with an energy that quantum mechanics forbids to be zero. The vacuum is the quietest those fields can possibly be. But quiet in quantum mechanics is not the same as still. Now, one of the most striking consequences of vacuum fluctuations is something called virtual particle creation. The energy-time uncertainty principle allows for energy fluctuations large enough to create particle-antiparticle pairs out of nothing, as long as those pairs annihilate each other quickly enough that the energy borrowed from the vacuum is returned before the uncertainty principle runs out of tolerance. The larger the energy fluctuation, the shorter the time it can persist. A fluctuation big enough to create an electron-positron pair can last for roughly 10 to the negative 21 seconds before the pair must annihilate. A fluctuation big enough to create a proton-antiproton pair lasts even less time. These virtual particles are not directly observable. They exist for too short a time, in too confined a space, to be detected directly by any instrument. But they are not nothing. They are real in the only sense that matters in physics, which is that they have measurable effects on things we can observe. The most famous of these effects is called the Casimir effect, and I want to spend some time on it because it is one of the most beautiful experiments in all of physics, a direct demonstration that the vacuum is not empty. Here is the setup. Take two flat metal plates and place them very close together, within a fraction of a micrometer of each other, in a vacuum from which all ordinary matter has been removed. No air, no gas, nothing. Just the two plates and the vacuum between them. Now, the quantum vacuum fluctuations I described exist both between the plates and outside them. But the region between the plates imposes a constraint. It is a bounded space. And in a bounded space, only certain wavelengths of virtual photons, those that fit between the plates as standing waves, can exist. Longer wavelengths are excluded. Outside the plates, there is no such constraint. All wavelengths can exist. So there are more modes of vacuum fluctuation outside the plates than between them. More modes means more vacuum energy pushing inward from outside. The result is a net force pushing the plates together, a force that arises from nothing but the quantum vacuum. No charge, no gravity, no material interaction, just the pressure of the nothing that is not nothing. The Casimir effect has been measured experimentally with great precision. It exists exactly as quantum field theory predicts. The vacuum pushes, the nothing presses, empty space exerts a force. But the Casimir effect, remarkable as it is not even the deepest consequence of vacuum energy. The deepest consequence is one of the most embarrassing unsolved problems in all of physics, and it goes by the name of the cosmological constant problem. Here is the situation. General relativity, Einstein's theory of gravity, describes how space-time curves in response to energy and mass. Any form of energy curves space-time. Matter curves it. Radiation curves it. And vacuum energy, the energy of empty space, must also curve it. According to general relativity, the vacuum energy of quantum field theory should have a gravitational effect. It should cause space-time to curve, and if it is large enough, it should cause the universe to expand. Now, here is where the embarrassment begins. When physicists calculate the vacuum energy density predicted by quantum field theory, the answer they get is enormous. Staggeringly, absurdly enormous. Depending on which cutoff scale you use for the calculation, the theoretical vacuum energy density comes out somewhere between 60 and 120 orders of magnitude larger than the observed value. That means the theoretical prediction is larger than observation by a factor of 10, followed by 60 to 120 zeros. This is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science by a very, very large margin. It is not a small error. It is not a systematic mistake in an experiment. It is a fundamental clash between two of our most successful theories, quantum field theory and general relativity, that neither theory can currently explain. We know the vacuum has energy because of the Casimir effect and dozens of other measurements. We know that vacuum energy should gravitate because general relativity says all energy gravitates. We know the universe is expanding at a rate consistent with a small positive vacuum energy because of the observations of distant supernovae that won the Nobel Prize in 1998. But the vacuum energy we observe through cosmology is incomprehensibly smaller than the vacuum energy that quantum field theory predicts. How is this possible? How can the quantum vacuum have so much energy and yet curve space-time so gently? Something must be canceling almost all of it out. Some mechanism must be reducing the gravitational effect of vacuum energy by a factor of 10 to the 120. But we have no idea what that mechanism is. We have no candidate. We have not been able to find a natural explanation within any existing theoretical framework. Some physicists have proposed that there is a symmetry principle that sets the vacuum energy exactly to zero, and that the small observed value is a correction to that zero from some other effect. But no convincing symmetry has been identified. Supersymmetry, which was for decades considered a leading candidate, requires a specific relationship between bosons and fermions that, if exact, would cancel vacuum energy precisely. But supersymmetry, if it exists, must be broken because the particles we observe do not come in the supersymmetric pairs the theory predicts. And broken supersymmetry does not cancel the vacuum energy. It just makes the cancellation imperfect, and imperfect by the full 120 orders of magnitude we started with. Other physicists have turned to the anthropic principle, the idea that the vacuum energy has the value it has because any significantly different value would not permit the existence of observers like us to measure it. A much larger vacuum energy would cause the universe to expand so rapidly that galaxies could never form. A much more negative vacuum energy would cause the universe to recollapse before stars could form and elements could be made. We exist in a universe with a small positive vacuum energy because that is the only kind of universe in which beings capable of measuring vacuum energy can exist. This argument is logically coherent. It is also deeply unsatisfying to most physicists because it does not explain the mechanism. It does not tell us why the vacuum energy has this particular value. It tells us only that we should not be surprised to find ourselves in a universe compatible with our existence. That is true, but feels like a surrender, like admitting we cannot actually answer the question. The cosmological constant problem is, in my view, the most profound, unsolved problem in fundamental physics. It sits at the intersection of our two great theories of nature, quantum mechanics and gravity, and it says with unmistakable clarity that those theories are incomplete, that there is something we do not understand about the vacuum, about space itself, about the nature of nothing. But I want to take you somewhere else now, somewhere that is perhaps even more unsettling than the cosmological constant problem, because I think it gets closer to the heart of what the impossibility of empty space really means. The vacuum is not uniform. I said earlier that vacuum fluctuations happen everywhere in space, but they do not happen in exactly the same way everywhere. The quantum fields that make up the vacuum respond to their environment, to the presence of matter, to the curvature of space-time, to boundaries and constraints. The vacuum near a massive object is different from the vacuum far from it. The vacuum inside a conductor is different from the vacuum outside it. The Casimir effect is one manifestation of this. But there is another, more dramatic one. In 1974, Stephen Hawking made one of the most extraordinary theoretical discoveries in the history of physics. He showed that black holes are not black, they radiate. A black hole sitting in the vacuum causes the quantum vacuum near its event horizon to produce a steady stream of radiation, now called Hawking radiation, that carries energy away from the black hole and causes it to slowly evaporate over time. The mechanism is deeply connected to vacuum fluctuations. Near the event horizon of a black hole, virtual particle-antiparticle pairs are created, as they are everywhere in the vacuum. But here, the immense gravitational curvature of space-time does something remarkable. It separates the pair before they can annihilate. One particle falls inside the event horizon, where it cannot escape. The other escapes to infinity, becoming real radiation that carries energy away from the black hole. The black hole loses mass. It evaporates. Hawking radiation has never been directly observed because for black holes of stellar mass and above, the radiation is far too faint and too cold to detect against the background of the cosmic microwave radiation. But the theoretical derivation is rock solid, and several analogs of Hawking radiation have been observed in laboratory systems designed to mimic the physics of event horizons. The vacuum, when subjected to extreme space-time curvature, can create real particles from nothing. The nothing is so energetic that gravity can pull real particles out of it. This is perhaps the most vivid demonstration of the impossibility of empty space. The vacuum is so full of potential, so charged with quantum energy, that a sufficiently powerful gravitational field can reach in and pull real, observable particles out of it. The nothing gives birth. Now I want to pull all of this together because I have been building towards something that I find to be one of the most important and most neglected ideas in the public understanding of physics. The impossibility of empty space is not a technical detail. It is a fundamental statement about the nature of existence. It says that existence is the default, that nothing is not a stable state, that the universe, at its most fundamental level, cannot be brought to rest. Think about that carefully. We often ask the question, why is there something rather than nothing? We treat nothing as the natural baseline, the state the universe would be in if left to itself, and we are puzzled by the fact that something exists instead. But if empty space is impossible, if the universe cannot settle into a state of true nothingness because the laws of quantum mechanics forbid it, then the question changes. The question is not why is there something rather than nothing. The question is why is the something arranged in the particular way it is? Nothing was never available as an option. The uncertainty principle took it off the table. The vacuum was always going to be full of something. The only question was what and how and in what configuration. I find this remarkable, not because it answers the deepest questions about existence. It does not explain why quantum mechanics has the form it has, why the uncertainty principle holds, why there are quantum fields at all. But it shifts the question. It pushes the mystery back one level and reveals that the mystery of existence is not the mystery of something appearing from nothing. It is the mystery of a particular kind of something, a universe with these specific fields, and these specific values and this specific structure rather than some other kind, the vacuum is not empty. It is the most basic form of full. It is what full looks like when you have removed everything that can be removed. And what remains when you have removed everything that can be removed is not nothing. It is the ground state of quantum fields, churning with zero-point fluctuations, virtual particles flickering in and out of existence, energy that cannot be zeroed out because the uncertainty principle will not permit it. Let me bring this home in the most concrete way I know how. Every atom in your body is mostly empty space in the classical sense. The nucleus is incredibly small compared to the size of the atom. The electrons are point-like. The vast majority of the volume of every atom is the space between the nucleus and the electrons. But that space is not empty. It is filled with the electron's quantum mechanical wave function, a probability distribution that extends throughout the atom and determines where the electron might be found. If you looked, the space inside an atom is not a void. It is a region of quantum probability, of fields in superposition, of structures that have no classical analogy. And the space between atoms, the space between molecules, the space between objects, the space between planets and stars and galaxies is not empty either. It is permeated by quantum fields in their ground states, by the vacuum fluctuations I have described, by the quantum fabric of space-time itself. The universe is not matter floating in emptiness. The universe is fields everywhere, with some regions where the fields are excited into particles and most regions where they are in their ground state, fluctuating, jittering, seething with energy that physics will not let approach zero. The space between your fingers is not empty. It is full of the ground state of every quantum field in the Standard Model. It is full of vacuum energy whose total gravitational effect we cannot explain. It is full of virtual particles appearing and disappearing on timescales shorter than anything we can directly measure. It is in the only sense that the laws of physics allow us to use the word empty about as far from empty as anything in the universe can be. There is something here that I find genuinely moving in the way that a physical fact can be moving when it connects to something deeper. The impossibility of empty space means the universe has never been truly quiet. Since the first moment of the Big Bang, before the first particle condensed out of the primordial energy, before the first atom formed, before the first star ignited, the vacuum was already full, already churning, already unable to rest. The quietness we perceive in the space around us is not the quietness of absence. It is the quietness of a ground state, the minimum noise of a universe that cannot be silenced because the laws of quantum mechanics will not permit silence. We exist in that noise. We are, in a very real sense, made of it. The particles that make up your body are excitations of fields whose ground state is the vacuum I have been describing. You are not matter floating in emptiness. You are a particular configuration of fields that are never truly at rest, arising from a vacuum that was never truly empty. In a universe that has never had access to the state we call nothing, I find that, all things considered, rather extraordinary. If this changed how you see the space around you, if you will look at the room you are in differently after this, drop a comment below and tell me what shifted. And if you want more of this, the vacuum that is not a vacuum, the fields that fill the nothing, the physics that sits beneath the physics you were taught, subscribe. We go slowly here because nothing, as it turns out, deserves more attention than we have been giving it.